Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back. So in the last lecture we were talking about stiffness under torsion, and we talked about different kind of cross sections and compare solid shaft with the thin tubes. So we'll continue with that, and now we talk about thin sheet under torsion. And if we take a small piece, a small a sheet with thickness T, and we try to twist. So yes, the way we twist, these are the forces we apply at the ends, and what we realize that, yeah, in one direction we see it will be the torque applied because of this twisting, the forces we are applying at the far ends corners. So F times L. So this is, if we see from one direction, it will be this. But what we also realize from the other end, it will be also same. So it will be, the T will be F times H, and the twist will be the same. So either way is the same. And when you talk about the torsional stiffness or the rotational stiffness, so we talk about the K here. So GK by L, and K is the, as we said, for circular cross sections is a polar moment of inertia, but for non-circular sections it's a different, and we have to refer to the references for that. And for these kind of sections, for thin sheets, what we realize, this K value is 1/3 area of the material we here, which is H times T, and the T square. And then if we talk about the rotational stiffness, where we have to apply the torsional moment M and the deflection, associated deflection phi. So what we find that this will come into picture. So it's a to the power q, and that's how we realize that it's torsionally not rigid and it's a very compliant. So whenever we are using this kind of element in the design, we have to be aware of. And later we realize that the sheets, many times they are used for compliance, not for stiffness. So now if we consider a open profile under torsion, so where we have a tube, but there is a slit, so it's a opening, so along the length. So if that is the case, and if we apply the torsion, the torque at the ends, what we realize that there will be deformation and it will slip. So you can see that even the edges, it will deflect. So it will not remain in the same plane. So actually the plane, the cross section, if we see, they are not in the same plane. And if we compare a open profile tube under torsion, then in that case it's very similar to a thin sheet under torsion. So that's why we compare. And what we realize that if you have this case, again we get this K as 1/3 A mat. A mat is the this one, the area, the actual material, T square, and this is the rotational stiffness, GK by L. So what he realized that again, if it's a tube but with open profile, it's not torsionally stiff, and under torsion we will we'll find that it's a very compliant. So if you want to compare the two sections, two kind of tubes, so in one we have a closed sections, closed tube, and then on the other hand, if we have the open one, so in the longitudinal direction there is a slit, so it's open, and when we compare the stiffness of the two under torsion, what we realize that if it's a close, the entire area, the enclosed area will come into the picture. On the other hand, if it's open, it's only the material, the area of the material will come into the picture. And if we compare the two, the rotational stiffness of open profile versus the closed tube, what we realize that there is a huge difference, and what we can find here is 1/12, and then A material versus A enclosed square. So this square term will make a huge difference, and from there also we can find that what is the implication if there is a cut or if the profile is open. So just to understand that, if we just take one example and take a circular tube, thin tube with the same dimensions, so diameter 100 millimeter and the thickness 1 millimeter, but one is closed and in another one is open. So in this case, if we compare, then the ratio of the areas, A material versus A enclosed, we can easily find that, because in one is a perimeter and multiplied by T for this case, and for the enclosed area is the closed surface area pi d square by 4. So if we do that, what we realize that this A mat versus A n will be 4T by D, and for these dimensions what I mentioned, it will be 1/25, and if we plug these values here, what we find that approximately the K open versus K closed profile is a 10 to the power minus 4. So it's a huge number, 10 to the power minus 4. So the open versus the closed, and if we just reverse it, we can see that if it's a closed tube, the rotational stiffness is very, very high. So closed, we can definitely use it as a torsionally stiff member, but if it's open, it's a compliant member. So if it's open and by some means if we can make it close, then what will happen? So I think we should be able to get the same stiffness. So what we have to understand that if it's an open section, it's along the slit, wherever is the opening along the length, they don't remain in the same place, but there is a relative movement. So if we don't allow that, probably we can achieve the same stiffness as the closed tube. So this is what I illustrated here. So stiffening by preventing relative axial movement at the seam. So if we just take thin sheet and wrap it, and we try to apply the torsional load, so try to twist, what will happen at the seam? There will be movement. And yes, definitely is a compliant member, is not rigid in torsion. But what happens moment we seize that motion by some means? So, for instance, if we just close the end, so just by putting a plate at one of the end and then welding it, what we realize that the relative axial movement we are not allowing, and therefore the torsional stiffness of uh, of this one will be equivalent to the closed profile. So this is one of the way. Of course, I think the length and d, the diameter, that's going to be critical, and maybe in order to avoid any kind of relative axial movement, maybe at few intervals we may have to weld it, tag it so that it doesn't move, and that way we can preserve the torsional stiffness. So even though the member is open, but we can still have a torsional stiffness, higher torsional stiffness, or what we can say, we can achieve the torsional stiffness of a closed section even with the open profile. Another way is we can have this kind of sections at the end. So we can have the thin sheet, and with this kind of profile, sawtooth, and when it's rolled, they interlock. And then again, because if it's an interlock, then this movement is not allowed, so it's not possible, and therefore if there is no axial movement at the seam, then even with the open section we can still achieve the stiffness of a closed section. So torsionally stiff shaft rolled from a stamp sheet, and definitely what we see here, if we use a stamp sheet, is the age of manufacturing, the cost, those are involved. If we just try to get tube, closed tube, it might be difficult and costly. But if we use just a stamped sheet and then roll it and get into this configuration, this will be very cost effective, but at the same time we can get a very stiff structure, a stiff tube, torsionally stiff tube, even with the open profile here. So what we have to also understand that even if it's an open profile, and suppose if we uh, seize the relative motion either by locking along the seam or locking the movement at the ends, many times we can achieve higher stiffness or stiffness of the closed sections. And many times these open sections we want because of the manufacturing, the age of production of these kind of sheets. What we also realize that this kind of we have many examples here. So different kind of profiles, and we have many folds, intersections, and if it's more than one, then what happens? They are compliant members in torsion, but by clamping the ends just like this, if we clamp it, we can get a very a stiff member, torsionally stiff member. Uh, so other thing is these profiles are also very good in bending. What happens if we try to twist it? There will be warpage as well because these are thin sections. So I think we have to be aware of. But what happens if we have this kind of cross sections, so profile cross sections, uh, with only one folding line? So we can see whether it's a L or plus or cross or T. Here the planes, the folding line, there is only one folding line, and in these cases, even if we clamp from the sides, we cannot stiffen because these are compliant, torsionally compliant, and they do not stiffen even if we repeatedly fix against torsion. So, even if we close the ends, we cannot stiffen it. And the obvious reason is under the torsional load, there is no warpage. So, many times it stays in a plane, and that's the reason it's a very difficult to stiffen them just by closing the end. So, these are compliant members, torsionally compliant, and unlike in the other case, if we have this kind of sections, it's a difficult. What we have to remember that all these profiles, whether one fold or many folds, these kind of sections are very good or very stiff in bending, torsion, and that's why many times it's used. But for torsion, we have to be little careful and check. So for if the number of folding lines are more than one, so two or more, in that case we can close the end, or we can seize the motion along the seam, and we can stiffen it. But that may not work with these kind of structures. So if we want to have a stiffer structure out of this, then we have to seize that motion, the rotation motion. And how we can do so? By just putting this bar or truss. So stiffening the torsionally compliant frame. So these are torsionally compliant if you apply a torsional load. So if you try to twist it, it can twist very easily. But moment we do, we can stiffen, because then it will restrict that deformation, and therefore we can achieve higher rotational stiffness. So if we want to use this even tubes, closed tubes, torsion, how to apply the loads? So usually there will be opposite loads applied at the ends, and suppose if it's just like this and you apply load like this, it tends to deform. So what to do? So in that case, so that's what is saying, preventing tube bending by proper force application at the tube face. So wherever we are applying the force, is very important to close the end. So for instance, here we can put this end plate so that the end cannot move, they cannot deform. So it's a closed, or we can have this diagonal member placed so that it ceases to have this motion. So we have to be careful, and moment we apply a load at the ends, we have to also check how it should be applied. Another very common example and common mistake, I would say, if it's a tube like column, so many times in the bigger structures, the tube kind of column we used, and for supporting any kind of vertical loads, one can easily make these kind of arrangements and then support the load. So just weld this kind of thing there, and then put the load. What we realize, that moment you have this kind of force supported on this, is trying to pierce through the surface. And what we realize, that the stiffness here is of the order of T the power Q. So it's a very thin tube, and normal to the surface, it's not stiff. It can easily pierce through, and it's not good design because it can easily. So what you can see is, in order to support this load, there will be this kind of force coming on the tube or in the column, and it can easily penetrate and damage it. And there are some examples, there are catastrophic failure, and many people died in the past. So I think whenever we have these kind of designs and making these kind of structure, we have to be careful. And if we have to really support some load, I think it's very important to have, so either it should be circumferential. So in this case is here on the edge, so you apply the load, but the loading is circumferential. So right, so forces here, so along the surface. So for circumferential load, the tube is stiff, or